Hi, we're now going to continue basic reinforcement learning, and we're going to get to deep reinforcement learning and some things that were done in 5 years ago, very dramatic still. And we're going to focus on Q learning, and I'll explain what that is. But first, I want to review last time, because you can take a whole course on reinforcement learning, and we're doing this as kind of a crash course really fast. So there are certain buzzwords, concepts that are important to remember. One is a policy, right? A policy is a way of stochastically selecting an action at a given state. Imitation learning. Imitation learning just means you've got expert behavior and you're just going to train the system to predict the action from the state. And it's just a cross-entropy prediction, just like predicting a label. Imitation learning. Imitation learning is off policy. That means that the data you're learning from is not drawn from the state distribution that you would encounter given the policy that you have learned. So on policy means your data distribution corresponds to your state distribution corresponds to the states you would reach under the policy you've learned so far. Off policy means you're learning from a state distribution not defined by the expert, not by your policy. Okay, off policy, on policy, that is important. The value function is important. The value function takes a state and assigns it a value. And that value can be relative to whatever your action policy is. Value iteration, this is the way of learning the value function. And value iteration updates the value function by setting the value function to the value you get if you pick the action that maximizes the discounted reward, assuming that the previous value function is correct for the future. So this is updating the value function, assuming that when you roll it out into the future, the one you have now is correct. Okay, review. Now we're going to talk about the Q function. The Q function is very similar to the value function. The only difference between the Q function and the value function is that the Q function takes both the state and the action. And it's going to give you an estimate of the value you're going to get if you start in this state and you take this action. Now, why do we have a Q function in addition to a value function? Well, the idea is we're going to start learning deep networks. And so this deep network is going to take some representation of this state and some representation of this action and compute a value. Now, this action can have features, right? This action can be a complicated thing, or just we could have a vector for every action that we're learning, like a word embedding. And if we give the deep network access to the action that we're taking, it can be more accurate, right? So by giving the function we're learning more inputs, we're going to improve its ability to model the reward. Okay, so this is analogous to the value function. It's just an expectation when we behave according to pi of our discounted reward when we start in this action, when we start in this state and take this action. And there's an optimal Q function, which is just the maximum over all possible policies of the Q function for that policy. And again, we have an optimal, the optimal policy can be defined in terms of this optimal Q function. The optimal policy is just maximizing the action at this given state that maximizes the Q function. And then we can actually kind of roll out the Q function. So the optimal Q function satisfies this property that's equal to your immediate reward, if you take that action, plus a discount gamma times the expectation over the next state, given that I'm taking this action at this policy. This is the state transition function. It's part of the world. And then since I'm recursing on the Q function, I have to also take the maximum, the best next action according to this Q function. Okay, so this is an equation that's satisfied by the optimal Q function. So Q function, you can define Q function iteration by simply letting this be the next Q function and this be the previous Q function. And that would define Q function iteration just like value function iteration. However, nobody talks about that. The reason nobody talks about that is typically value iteration and Q value iteration are defined for finite state spaces. So already they're not terribly interesting because the state spaces one is interested are if maybe they're finite, but they're at least exponentially large, which means that they're not really finite. It's infeasible to iterate over them. But even in the case of finite state spaces, this Q function iteration is going to end up taking state squared times action squared steps to do one iteration, whereas the value function is just s squared a, so it's more feasible. So now we're not going to do Q function iteration, we're going to do Q learning. And Q learning is based on something called the Bellman error. And the important thing that you'll hear in the literature is Q learning, not Bellman error. So this is the phrase you want to remember, Q learning, but it's based on the Bellman error. So what is the Bellman error? I've got a Q function that's estimating the value for a given state action pair. And I can also estimate this value by rolling it out one step. So what does it mean to roll it out one step? Well, this is to roll it out one step, I take my immediate reward and then plus a discounting of the expectation over the next state, given I'm taking this action, of what the Q function thinks is the best action at the next state. Okay, this max over the next action is just picking the best action that this Q function thinks is the best action at the next state. So this is a rolled out estimate. This thing inside the parentheses here is a rolled out estimate of the Q function, and it's more accurate because it's reducing the dependence on the Q function to only look at the next state. And the Bellman error is the difference between the Q function not rolled out and the Q function rolled out. And the idea is, as I said, the Q function rolled out would be more accurate. So if this was Q star, this difference would be 0. And so that's the theorem. If the Bellman error is 0, then you are at Q star. You're at the best. Now, this does not say that this gradient descent algorithm converges necessarily, but it says if it reaches Bellman error 0, then you're good. And then you can get an algorithm. You generate pairs from the policy. The Q function defines a policy, right? You can always take argmax A of what the Q function thinks you're going to get if you take A, right? So if you've got a Q function, it defines a way of acting, a policy. So I can generate pairs from the policy implicit in the Q function. And then given this set of pairs, each pair defines a Bellman error, right? The Bellman error is a function of a pair of state action pairs. So then I can update my policy in the direction of reducing the Bellman error. That is Q learning, right? You're updating the policy to reduce the Bellman error. Okay, it has issues. Problem 1 is nearby states in the same run are highly correlated, right? These are two adjacent states. We're going to be looking at a nice video of a game called Breakout. And it's very clear that in this game of Breakout, two adjacent states are very similar. Not much, it takes a while for the state to change in some really big way. So we're not getting independent draws from the state when we do this. A more serious issue, I mean, we could always draw, tons of states, but it can take more. A more serious issue is that this Bellman error training tends to be unstable. And let me try to explain, at least this is my understanding of what causes this instability. If I'm running at a policy, that policy has a distribution over states that I encounter when I act according to that policy. What happens is a lot of states and maybe a lot of actions aren't used. You don't reach them. So you're not really anticipating very well what will happen if I change my policy, and suddenly I can change my policy just a little bit, and suddenly the state distribution and the optimal action distribution changes significantly, right? You sort of get this amplification over time of a small difference can lead to a very different state distribution. So if you've just trained on policy, then your modeling of the states and actions that you're not taking is bad. And that might lead you to think that some other policy might be better, but it's only because you haven't modeled the distributions at that other policy. So you shift over there, and then you realize that's bad, but you stop modeling the old policy, and then you shift back. So you can be moving between policies. Each policy stops modeling the consequences of the other and then thinks the other is better. And it goes back and forth. Anyway, that's my intuition. Empirically, it's unstable. It tends not to converge. So this problem is addressed by something called a replay buffer. That's a word, a phrase, a bigram you want to remember, replay buffer. So when you use a replay buffer, what you're going to do is have a database, a replay buffer of these 4 tuples. And these 4 tuples are going to consist of a state and an action, and a reward, the state, the action, the reward, and the next state. Okay, and I'm going to store, as I'm learning, I'm going to build a database of these 4 tuples that I have encountered under some policy as I'm learning. And then what I'm going to do is repeatedly run the policy implicit in my current Q function. So I'm also going to have a current Q function, the current setting of my deep network. And as I run according to my current Q function, I'm going to add tuples to the replay buffer. So I'm always running add a policy implicit in the Q function and adding to the replay buffer. But that replay buffer is going to contain these 4 tuples from earlier Q functions, from earlier policies. And I'm going to maintain, as I'm learning, I'm going to maintain this buffer. I'm going to limit the size of this buffer. So as tuples get old, stale, they'll get taken out. So there's but the buffer is containing a long range history of 4 tuples that I've encountered under some policy. And so I'm repeating this. So I take a run, then I remember this policy, right? I set psi equal to this policy. And then given this policy, the update I'm going to do on my parameters, on my policy, is going to be an update based on holding this policy fixed and looking at the rollout values, looking at the Bellman error. Sorry, this is the Bellman error defined by a random element of the replay buffer. So the update is going to be drawing from the replay. Okay, so let me back up. I've got this replay buffer that is accumulating over many different values of my network, over many different policies. I'm going to get many different policies by running at the policy implicit in a Q function. Then my update is going to be based entirely on the replay buffer. So the update is going to draw elements of the replay buffer and compute a Bellman error for that element of the replay buffer. And that Bellman error is going to be the difference between the Q function as defined in my current policy, current Q value, minus a rollout value based on a fixed psi. So as I'm learning, as I'm updating this, as I'm doing a bunch of these updates, I'm holding this psi fixed. So it means I'm sort of off policy. I'm off policy in two ways. I'm keeping the psi fixed and I'm drawing data from the replay buffer, which is almost like, yeah. So I said this, the replay buffer is a mixture of policies. And replaying from a mixture of policies addresses this stability problem, right? My data is drawn from a mixture of policies. It's not focusing on one policy. This also seems to be related to the fact that, or to the difference between the case where the optimal policy is deterministic. Because if the optimal policy is deterministic, then running on policy is very focused on a particular action selection. And we'll come back to that. Okay, so there's some variations on this. Multi-step Q learning. So Bellman error is based on a one-step rollout. I can also define a Bellman error based on a D-step rollout. I just take the discounted reward over D steps into the future, where the discounting is keeping track of how many steps into the future I have. So this is multi-step Q learning, just a more accurate Bellman error by rolling out further. I can also replace the replay buffer with asynchronous Q learning. So in asynchronous Q learning, I've got a bunch of learning processes. Each one of them is running at some Q function. So it's generating data from the implicit policy defined by a Q function. But all of these asynchronous processes are using different Q functions. And that causes the update, the updates that are coming from all of these asynchronous processes to be drawn from many different policies, and that's similar to the replay buffer. So it's replacing the replay buffer by a bunch of asynchronous processes that are asynchronous in the sense that they each drew a Q function at different points in time. So that's what it means to be asynchronous. And because they're drawing the value of the Q function at different points in time, these asynchronous policies are all running, asynchronous processes are all running at different policies. Okay, so those are twiddles. So this is a paper that appeared in 2015. The results are still dramatic. And this is called a deep Q network. So it's running the replay buffer version. Asynchronous was a slightly later paper, but this is playing Breakout. So what's happening is they simulated these old Atari games from the 70s, 1970s, and they fed the actual screen, the image, into a convolutional neural network, and that convolutional neural network is trained by Q learning, right? So it's going to be trained by Q learning to select the joystick action, 1970s. And now what we're going to do is switch the screen share. And we're going to watch this thing learning. Okay, so it's going to start out, it's doing this Q learning based on a replay buffer. So it's going to play Atari Breakout. And it's not given anything except the screen and the score and the reward score that the screen shows. No domain knowledge. Convolutional neural network. 10 minutes of training. It sort of can hit the ball back, or basically random. This is 2015. Let's learn to play. All right, and then something magical happens. It's learned a trick. Boom. All right. Okay. In the next unit, we're going to continue with yet more sophisticated learning algorithms. Thanks, everybody. Next time.